Hello everyone, my name is Mohammad Sarmad Mir. I am working as an early stage researcher in Marie Curie ITN project Enlighten. Today, I will present you our research with title Passive LiFi, Rethinking LiFi of our low power and long range RF backscatter. My co-authors include Borja Genovas and Domenico Agostiniano from India Networks and Ambush Varshne from Uppsala University. In the last decade, the IoT market is rapidly growing. Many leading companies, including IBM and Cisco, estimated billions of IoT devices to be installed worldwide. But if we see the current state of IoT devices, we see the sales are not that high. We come to know that the actual deployment is lagging behind the predicted values. There are many reasons for that. One of them is the self-sustainability of the device. IoT devices are interconnected and exchange information. They need energy to perform different tasks, for example, sensing, communication, etc. Now, if we use batteries to power up billions of IoT devices, there are certain drawbacks to it. Batteries need manual inspection and replacements. The exhausted batteries produce huge amount of waste due to chemical composition of the batteries. That can lead to overall reduction in vast deployment of IoT devices. So here the question arises, are batteries necessary? In past few years, we see several devices that operate on harvested energy from the environment. For example, solar-powered eye tracker harvests energy from ambient light. Also, we can harvest energy from radio frequencies. Another source of energy is a chemical energy that we can harvest from natural metabolism of certain kind of bacteria, or we can use thermal energy that can be useful, especially harvesting energy from body in wearable devices. Our approach is to use light energy. Why? As we have pervasive lighting system deployments around us. Also, we get more homogeneous harvesting with respect to the location. And light can be used for multiple purposes, for illumination, communication, and also harvesting. For uplink, we use RF backscatter technique because of its energy efficiency and absence of power-hungry active radio for transmission. In recent time, there are different systems who are utilizing different approach for design of battery-free devices. For example, Edison, they are also using VLC and RF backscatter, but they are prone to short range and they are using non-optimized VLC receiver and also power-hungry components such as oscillators. Another system for localization based on chips is presented by Nanda Kumar. They also use oscillators in IoT devices, which I said they are power-hungry components, and they reduces the lifetime of the device. There is no downlink, and also there is no data in the uplink. They are shifting the frequency of the incident RF signal for localization. In passive VLC, they are using VLC for uplink and downlink. They have a low uplink range and using multiple photodiodes and different amplifiers, which requires a lot of energy expensive signal processing. In state of the art work, there are different challenges. For example, most of the work they are using the oscillators, which are power hungry components. They are using multiple solar cells for harvesting and communication. There are different solar cells for communication and different for harvesting. Also, the modulation scheme is very important for uplink. If we use a simple modulation scheme, they are easier to implement, but they are energy efficient, but they are short in range. For complex modulation techniques, they are preferable, but they are hard to implement. They are power hungry, but they are robust to interference and noise. So to address these problems, we are exploiting chirps. Chirps is a signal that changes in frequency with time. So it can be either increasing frequency, which is up chirp, or decreasing frequency with time, which is a down chirp. There are different systems who are utilizing chirps, for example, LoRa, to get higher range by demodulating the signal below the noise floor. Also, chips are robust to multipath, but they are energy expensive. We are addressing this problem of energy by offloading the chips from tag to the infrastructure. We are utilizing light chips by modulating LED with varying frequency. Our chips provide uplink clock for uplink. We are able to achieve long range, and also they are energy efficient as we are dedicating the generation from tag to the infrastructure. So here is the overview of our system. Think of a room in which we have a lighting network, and we are having a battery-free IoT device and a RF router located anywhere in the building. For downlink, we are using the visible light communication by modulating the world with the different modulation schemes and messages. For uplink, we are using chips, which are varying from frequency F1 to F2. And these chips are then used as a carrier to enable the backscatter communication. So they are providing the clock, the chips are providing the clock to enable the uplink backscatter communication using chips. And we are using it in a time division multiplexing fashion using LiFi packets and then sending the chips to enable downlink in T1 and uplink in T2. Now I will discuss about the system design. We have a LiFi transmitter. The main purpose is to provide illumination. It provides energy for harvesting, and then communication, downlink communication, and also it provides the baseband for uplink. We have used a modified version of OpenVLC 1.3. OpenVLC is a known platform in research community for visible light communication. We modified it to a current control switching, which helped us to achieve 10x more illuminance at 1 meters. And also, we are able to get sharp waveforms, which are really required for recovery of the baseband signal at the tag, because we need accurate recovery of baseband to enable uplink. And also, by having a symmetrical signal, we can have a simple and energy efficient RF receiver, energy efficient downlink receiver on the tag. In our IoT tag, we can even see the hardware on the upper side, and then we have a schematics for the IoT tag. We are using a single solar cell for communication and also for harvesting. We exploit the fact that communication requires to take modulated signal and harvesting requires constant signal. From their different approaches in which they are using different slices of time, for different slice for harvesting and different slice for communication. We aim to use it at the same time, both communication and harvesting, without losing any energy that could be useful for harvesting. However, the photonic community has always considered this unrealistic because of how photodiodes work. Fundamentally, in order to receive data, photodetectors are biased in reverse mode. In contrast, when the photodetectors operate in photovoltaic mode, to harvest energy, it is positive bias, and hence the voltage is with opposite signs with respect to communication mode. In this work, we present a new low-power LiFi receiver to solve this problem, leveraging the fact that communication and harvesting use different frequency components of the same signal. Also, we are using high-pass filter to separate the modulated component and low-pass filter to get the DC component to facilitate harvesting. Here we can see that the R2, which is the resistance with low pass filter, is important. There is a trade-off in selection of R2. If we increase the higher value of R2, then we get a better communication. If get for a lower value of R2, we get a better harvesting. Here we can see that there exists a trade-off between harvesting and communication, especially when we connect to increase the size of solar cell. If we connect the same solar cell in series, we can see we get a better communication, better peak to peak voltage we get. And if you put it in parallel, we get better harvesting, so less time to charge, which you can see from the plot on the right side. We started with 6 solar cells. We evaluated them with respect to time to charge and we peak to peak. And with Pareto optimal analysis, we selected a particular solar cell. For more information about how we selected the solar cell, you can have a look on our paper. Also, we presented a dynamic configuration. For example, if we detect this configuration depend upon the environment. So if we think that there is sunlight or we have enough energy for harvesting, we can connect most of the solar cells in series to facilitate communication. And in case, for example, at time we don't need communication, then we can put the solar cells in parallel to facilitate harvesting. Next is the backscatter module. And we are using the optical chips and converting them to the electrical chips. There is a frequency shift in backscatter to help it not to get interference from the carrier signal. Also, we are using a backscatter receiver, which is the same way as we use with the LoRa signals, which de-chip the received signal by multiplying it with a conjugate chip. And we take a fast Fourier transform to get a peak bin of a constant frequency. If we get a peak bin, we take it as a bit 1, otherwise we take it as a bit 0. Now I will present the evaluation of our work. This is the evaluation of the thresholding circuit. As you can see that our thresholding circuit is robust to background illuminance, and we get a symmetric output. And as I told, if you compare the design and our work is presented in red, we get a more symmetric signal, which helps us to recover the baseband at tag more efficiently, and also we can implement a very simple LiFi receiver on the tag. We are able to get a higher range as known as 3.5 meters compared to 1.5 meters in Edison, and we are able to get around 280 kbps downlink data rate. For uplink, as we are using chips, so we're able to decode the signal around 17 dBs below the noise floor. And there is a trade-off between the spreading factor and bandwidth. So if we increase the bandwidth, SNR limit also increases. And we can see it here with the highest spreading factor, we get the best results. For uplink range, we did different experiments indoor in our building and also outdoor in a ground. So for indoor, we are able to get up to 40 meters of range with a lot of walls in between the communication, in between the tag and the receiver. In outdoor, it was more clear path, line of sight, and we are able to achieve up to 305 meters of range. For uplink consumption, we get a very good results, and for uplink efficiency, we get better results than previous works. As compared to LoRa Backscatter, Edison, in our work, we get 80.3 meters per microwatt, as we have offloaded the oscillators and offloaded the generation of chips to the environment. We have a very energy efficient RF backscatter module, and we get a very good efficiency and power and the range per power. Also, we did some experiments for self-sustainability. Normally, the battery-free devices are in sleep mode most of the time, and they are active for a very shorter time. But in this work, we present that we can achieve a continuous communication without exhausting the battery. So we don't need to charge the battery. It keeps, if we can have a 250 bps continuous downlink, or we can have 1 kbps downlink in the interval, and we give also time for uplink, as uplink is more energy efficient. So we are able to achieve higher data rate in downlink without need to charge the battery under the normal lighting condition of 500 lux. So just to conclude, in passive Li-Fi, we are using visible light for Li-Fi transmitter. We are backscattering and receiving signal, decoding signal well below the noise floor, and we achieve power consumption of in microwatts. We are able to achieve more than 305 meters of range. So our system enable long range and low power communication, for example, greenhouses, home automation, and smart cities. Thank you very much for listening to the presentation. I'm open to take any questions. Thank you.